All right, this is going to be the video for section 3.2 for differential equations on using nonlinear differential equations as models, first order nonlinear models. All right, if we open up our differential equations to having nonlinear coefficient terms or other variations, that means that the differential equation no longer qualifies as a linear differential equation, as we saw in 3.1, then we can model a wider variety of scenarios. The downside is that most of the methods that we know so far to solve differential equations work on only linear differential equations. So the main method we know so far that worked with nonlinear differential equations is just the first one we learned, separation of variables. That's more generic, but that isn't always possible. Later in the course, we're going to learn additional methods that will also work with nonlinear differential equations. And we can always resort to some kind of numerical method or computer software to find approximate solutions as well. So unfortunately, when the differential equations we're using to model a scenario are nonlinear, often the solutions are much more involved because the integrals needed get more complicated, sometimes enough to require an integral table or partial fraction expansion or other kinds of methods. But nonlinear differential equations can model a variety of interesting scenarios. So because they're more complicated, we're going to focus on fewer of them, and we'll just look at two complicated examples here to illustrate. But they're also interesting, useful examples. So the first one is, let's look at falling masses. So if you have an object, a mass that's falling, it's subject to Newton's law of motion, which is F equals ma. Any force on it equals the mass of the object times the acceleration of the object. And so how it moves is determined by what forces are applied and then the mass. You can think of the mass as something resisting acceleration, a resisting force causing an acceleration, right? So it's easy enough to work with this if you're in a vacuum where you're disregarding air resistance, right? But in the real world, uh, if you're on the surface of the Earth, there's an atmosphere, and so there's another force involved besides just gravity. So first, let's consider just gravity. The mass here would be specified either in kilograms in the metric system or slugs in the imperial unit system. And then for Earth, the gravitational constant is 9.8 meters per second squared metric and 32 feet per second squared in the imperial system. And we also know that if we specify a position of the object as a function of time, s as a function of t, where s is position from some defined origin, then the velocity is the derivative of position, and the acceleration is the derivative of velocity, which is therefore the second derivative of acceleration. Okay, so if we take Newton's law, F equals ma, I'm just going to reverse it here, ma equals F. And if the only force is gravity operating on the object, which I'm going to label Fg, well, gravity is just a force, so it's mass times an acceleration. Gravity is really an acceleration, right? So we use m times the gravitational constant. So Newton's law is saying that ma, where a is the acceleration of the object, is equal to the mass times the gravitational constant that the object is undergoing, right? But we know that the acceleration is the derivative of velocity, right? So I can write this a as dv dt, right? So m dv dt equals mg. So this is like saying ma, the acceleration of the object, is equal to a force, which is currently gravity, and then writing out an expression for that force. All right, so what happens if we more realistically include the fact that in the atmosphere on Earth there's air resistance, right? And air resistance always opposes motion. It's in a direction which opposes motion, right? So in general, the faster an object is moving, the more air resistance is experienced, right? But we can model that using different models for air resistance. So if I'm going to put that into my differential equation model, I'm going to have my ma is equal to the gravitational force, but then also I'm going to combine in some way the acceleration of the air resistance, right? And regardless of which way the thing is moving, the air resistance will always be negative to the direction of motion, right? So this term at least will always be negative. This will be positive or negative depending on how you define your coordinate system. Okay, so what do we use for this air resistance force? Well, we can make an assumption that the air resistance is proportional to the velocity. In other words, as the speed goes up, the force pushing back goes up linearly, right? And then we could model that as just some proportionality constant times v. And if we did that, we would get a linear differential equation, which we could solve using methods we talked about in 3.1, right? But that's actually not very realistic. It turns out that when people measure air resistance, it really behaves this way as proportional to the square of the velocity. So if something is moving twice as fast, there's 4 times as much air resistance, not twice as much air resistance. And if it's moving 3 times as fast, there's 9 times as much air resistance force. So a more realistic model is to model air resistance as proportional to the square of the instantaneous velocity. And so that means this term here would be kv squared. And that, because of the square here, results in a nonlinear differential equation that we solve. Okay, so let's take a specific example and we'll see how this looks. So if we had a 16-pound cannonball and it's shot vertically upward from the ground with an initial velocity of 300 feet per second, if we assume that the air resistance is proportional to the square of an instantaneous velocity and the constant of proportionality is 0.0003, first, could we solve the differential equation that would give us the velocity versus time? And then secondly, could I answer the question, how high would the cannonball be 4 seconds after the launch? This time we're including air resistance, right? All right, so the first thing we'll do is set up our differential equation, which is going to be ma equals gravity, and then also we'll have a term in here for the air resistance, okay? And let's define up as the positive direction, which means that my gravitational force will be pushing in the negative direction. So I'm going to write negative mg here for the gravitational force, and then also negative kb squared, because that always opposes the acceleration of the object. All right. And if we wanted to rearrange that, so that we're going to say this is m dv dt equals negative mg minus kv squared. If I wanted to rearrange that to be able to separate the variables, I could multiply both sides by dt first, and then I could divide by the entire thing that's multiplied by dv dt, and then maybe divide both the sides by negative m to move the m on the bottom over here. So I would get 1 over mg plus kv squared dv. V is over here and a constant. And then I've got some other part of the constant over here, dt. It just turns out to be efficacious in terms of solving to split it up this way. All right, so to go further here, the integral is going to get pretty complicated and we're going to end up using an integral table. But there's some more manipulations we can do. So here's where we left off. The next thing we're going to do is we're going to factor out a k from the bottom here. Okay, we're going to factor this k out on the side. And when we do that, that means we end up with mg divided by k here, but the k disappears from this. And then I'm going to move that k separate from this whole fraction to call it 1 over k. And then I'm going to try to make this, because I know I'm taking an integral eventually of this. I'm going to try to make this match an integral table of some kind. This one's going to be easy because it's just a constant dt, right? That's going to be easy to integrate, but this is the problem over here. So one of the forms is I see I have the variable squared here and a constant here. So there is a form that says that the integral of du over a squared plus u squared is 1 over a inverse tangent of the variable over a. So that means I have to represent this as variable squared and this is variable squared. So to make that work, this is already variable squared, but this mg over k, I'm going to write it as the square root of mg over k, and then that's being squared to form this, so that this square root term in here is the a, okay? All right, so now that I've rearranged it like that, I'm going to take the integral of both sides. The right-hand side integral is real straightforward. This is just a constant times 1. Integral of 1 is the variable, which is t, so it's the constant times t plus an integration constant c. Okay? Over here, I'll ignore this for right now. Let's just work with, we'll tack that back on at a good point later. So we've got this on the right-hand side. The left-hand side, this integral here is an inverse tangent integral. So I'm going to replace it with 1 over this constant, 1 divided by this constant times the inverse tangent of the variable, which is v over the constant. Okay, so I had to use a table to integrate this. Okay, and then I'm going to work with this constant a little bit more to do some simplifying. So since I've got a square root on the bottom here, if I wrote this k as 1 over the square root of k squared, I can move the k squared inside the integral here when these are multiplied. And then this k will cancel one of these. So I end up with 1 over the square root of kmg. So I have 1 over the square root of kmg. Inverse tangent of this equals negative 1 over m times t. And I've got an integration constant, but I'm going to wait till later to add it. It fits better if I add it later on. Okay, continuing to manipulate. If you then multiply both sides by one by square root of k mg, then it removes from this side. So multiplying both sides by this, by this. So multiplying by a square root of kmg here, so that both sides are um, we get rid of that from the tangent term, inverse tangent term. Then I get this term, which is a negative 1 over m times square root of kmg. And again, to try to move this in, I'm going to write this as 1 over the square root of m squared, so I can move it inside the radical, and then this will cancel one of these. So I end up with negative square root of kg over mt. Okay. And finally, now I'll go ahead and tack on my integration constant. All right, so now I've got this. And the reason why it's legal to do it at that point is so far I've only been multiplying and dividing by constants, not by variables, so we're good. Okay, to undo this inverse tangent, I'll take the tangent of both sides. So you have to take the tangent of both sides. That makes it go away over here, but then I have the tangent of this quantity, and the c is inside the tangent. And then finally, I could multiply both sides by this to solve for v. So I have velocity as a function of time. And this is my general solution at this point, because it was the differential equation where it was the derivative of velocity. So now I have an expression where I can plug a time in and find the corresponding speed of the cannonball. I haven't established this yet, though. So I'm going to need initial conditions to do that. So the initial conditions are that there's an initial velocity of 300 feet. So when velocity is 300, when time is 0, we have mg that's the gravitational force, is the weight of the object. Weight is 16 pounds. And since g is 32, if you solve this for mass, then that would mean that the mass is 16 over g, which is 16 over 32. So it's 0.5 in the units of slugs. So a half a slug is the mass. And then our constant in proportionality was given in the problem as 0.03. So if you plug all that stuff in, I'll plug all these constants in, as well as 0 for time and 300 for the velocity. You can carefully solve this for the constant c. You'll end up getting that c is the inverse tangent of 300 over 230.94, which turns out that this c constant is 0.9147. I'm including a lot of decimals here so that if you do this yourself, you can check to see if you're doing it right. Okay, then you can go back to the original differential equation and plug in the c, right, and the other constants here. So all of these constants here to finally get this as the final form in decimal, where I have all the numbers expressed as decimal. So this is the solution. That means I can now plug a time in, and I can get the velocity of the cannonball at any point in time. Okay, so that's the end of part A. It asked us to solve the differential equation for the velocity. In part B, it says, how high would the cannonball be 4 seconds after launch? So now the question's asking not about speed, but about position. So we're going to have to find the position function. And since v is the derivative, the velocity is derivative of the position, to find the position, we're going to have to integrate the velocity. So if I've got my velocity here, and I went back to general symbols here for a second, but we could use the numbers if we wanted to. Then the position is the integral of that velocity, right? So this is a constant, so it comes out, but you're going to end up taking the antiderivative of a tangent of an argument here. To make it easier to do this integration, I'm going to replace all these symbols with some new symbols. This right here, I'm just going to replace that with a, and I'm going to replace this constant here with b. Okay, so I can rewrite this as the position is a integral tan of negative bt plus c dt, and I'll do this integral here. So we can do that with a u substitution. I'm going to substitute the argument of the tangent as u, which means that du will be negative b dt, or dt is negative 1 over b du. When you substitute back in, you get a integral of, and then this just becomes tangent of u, and the dt is negative 1 over b du. Right, you can bring the negative 1 over b outside, so you're just taking the antiderivative of tangent, which you could look that up in a table, is the natural log of the absolute value of secant of u. Okay, so, but because of log properties, I could take this negative here and move it up. so that it's the natural log of secant of u to the negative first power, but 1 over secant is cosine. So it's also possible to write this as positive natural log of cosine plus some integration constant, which I'm calling k to avoid colliding with this c. Okay, then we'll substitute what u is. So I finally end up that the position is a over b, natural log of absolute value of cosine of negative bt plus c, and then plus an integration constant. Okay. All right, so if you plug back in what a and b were, you'll get this, a here, b here, and b here. Over here on the left, we can put this all under one radical, say dividing by a fraction is multiplying by its reciprocal and seeing that these cancel to get that this is the square root of m squared over k squared. That's what's going on here. And then we have now a general solution, but we need to figure out what the values of the constants are, right? When we did the initial value problem before, we solved and figured out that this c was based on the velocity initial condition, and that was this constant. So I'm going to go ahead and fill that in as well. But now I can take another initial condition that if the ball is on the ground at the beginning, that means when time is 0, distance is 0. It says starting upward from the ground. So there's another hidden initial condition given here. And if I plug 0 in for position at time 0, that will allow us to carefully solve for this constant, which turns out to be 823.8 about. So if you plug all of that in, that gives me now a generic solution for position as a function of time. And wow, is that complicated. So just adding the air resistance term makes a physics problem a lot more complex, right? But now I can answer the question. It's how far will the ball be off the ground at 4 seconds? So I simply plug in 4 for t and then compute this in a calculator to get that this is 713.12 feet. All right. So substantially more complicated when we introduce a nonlinear element, which is why we're not going to do a lot of it in this class, but it's good to know that it exists. So that's the first example of the two I want to show you of nonlinear systems or nonlinear differential equations to model scenarios. Okay, let's take a look at the second example. Maybe not quite as complicated as the first one there. This one's called logistic growth. Okay, so we're exposed to what are called logistic curves at earlier points in our math career, but we haven't really seen where they come from. And they come from this modification of the growth model. So if we know we have unrestrained growth, that can be modeled using a linear differential equation, like the rate of change of a population is proportional to the population. But more realistically, things like natural resources limit growth, right? If you're in a forest, right, deer can't just grow forever, right? Because eventually they eat all of the foliage, right? So there's going to be limited food, limited water, predators, or something like that that are going to limit the ability to grow, right? So what you can do is you can assume that there's some maximum number of individuals that the environment can support, and that actually has a name. It's called the carrying capacity. We usually call it K. Okay, so if you start with this assumption and you just move this p to the other side, what this equation is really saying is if you take the ratio of how fast a population is changing to the current value of the population, it's equal to a constant, right? So our unrestrained growth model is saying that the ratio of the speed of growth to the population is constant. But a more realistic way to model this would be to say this is not constant, and this ratio will depend upon where you are in the population curve. So if you replace this constant with a function of the population, there's different ways you can model that, right? You can say, all right, I have a function, right-hand side function that varies with population versus population. And maybe you could say the carrying capacity is here, right? So the function has to go to 0 once we've got the population to the maximum allowable amount, k. And so we could also specify if that's an x-intercept, a y-intercept, and just call that r. We're just going to call that r. And then there's different sorts of function curves that scientists use to model the way a population behaves throughout its as it approaches carrying capacity. You could have some complicated function. You could have a linear function like this. And we're going to look at what happens if you assume this linear curve here. Okay, so if you assume the simplest model for that, which is a line, then that means that this function would be just r minus the slope k over r times p. Okay, and that means that's what would be placed over here instead of a constant. So you'd have r minus k over rp. All right, and if you then remultiply both sides by p, you get the differential equation dp dt is equal to p times r minus k over rp. And typically what they do is they just replace this r now with a new constant called a, and this k over r is replaced with a new constant called b. So this model here is the differential equation for what's called logistic model growth. It means growth subject to a constraint on the upper end by the environment. So what would the solution of this equation be? Well, if we wanted to solve that, let's rather than solve it generically, let's solve it with a specific example. So let's say that you're in charge of a chain of supermarkets that are nationwide, and you're rolling out a new computerized checkout system. Okay, but we don't assume that that the growth of the number of supermarkets in which are adopting the new system is going to grow unconstrained. Let's assume that the model is a logistic growth model that has some sort of a resource end, right? In fact, there would be because there's only so many supermarkets, right? You can't have more supermarkets adopt the checkout system than you have supermarkets, right? So if we were to use dn dt equals n times, I'm just saying this is n times a, did I have minus there? Yeah, a minus b p or n, okay, except that I'm filling in the constant 1 for a and the constant 0.0005 for b. It says we're going to assume that the number is, for some reason we've done analysis and believe that this is valid. Okay, we have to have an initial condition too, and that's going to be that when we start at time 0, a single supermarket has adopted the checkout counter system, and we want to see how this new system is spreading throughout our system of supermarkets. Okay, so first question asks, use a phase portrait to predict how many supermarkets are expected to adopt the new procedure in the long term and sketch the predicted solution curve. So this particular differential equation, it's nonlinear because it has an n times n and n squared term, right? But it is what we call autonomous, right? It's an autonomous equation because the right-hand side is only a function of the y variable, which means if we can find the zeros, those places will be places where we have critical points, right? So n equals 0, and whenever this term is 0, which happens at n is 2000, is our critical point, 0 and 2000. So what happens to the solution curve? Well, if you plug in values in the regions above and below, I'm not going to bother with this region because you can't have a negative number of supermarkets. But if I plug in this region, I take a value like 1000 that's between 1 and 2000 and plug that in here, you end up getting a positive number. Right. And so that means that all the slopes are positive in this region. The phase port would have positive slopes. And up here, if you try a number above 2000, like 3000, plug it in here, you're going to get a negative number, which means the slopes are negative, right? Right. So the solution curve in this region would be rising from an asymptote of here to leveling off here. And if you happen to be above that, then it would go down like this, right? All right, so we're predicting that since we're starting here at n is 0 right here, at 1 right here, we're predicting that what's going to happen is this curve is going to slowly, the new checkout procedure is going to spread slowly at first, then rapidly, and then it'll level off as we approach really 100% of the supermarket checkouts. And this model basically says we're never quite get to 2000, right? All right, so that's what that would look like if I just used the phase diagram, but let's actually solve the differential equation itself. So if I want to solve this, I could use separation of variables, multiply both sides by dt, and then divide both sides by everything else, and I would get this. Okay, rather than trying to resort to an integral table, let's use partial fraction expansion because this denominator is already factored. If I wanted to use partial fraction expansion, I could go online and use one of those calculators. And that turns out that that this is equivalent to two terms, one of which is 1 over, or in this case, n, 1 over n. And the other one has is this, negative 0.0005 over 0.0005 n minus 1. So I'm just going to copy what the partial fraction expansion gives me here. And that separates this into two easier to integrate terms. Okay, this one's going to be easy enough. That's going to be natural log of n. But before I do this side, let's multiply top and bottom by 2000 because that's what 1 over 0.0005 is. That just makes this negative 1 over 1n minus 2000, and then I'm going to move the negative outside. For this integral here, we'll use a u substitution in the denominator. U is n minus 1, so du is dn. So this just ends up being the natural log of n minus 2000, and the first term is the natural log of n. Absolute value equals, on this side we have the integral of dt, which is just t plus an integration constant. Okay, so here's the implicit solution to the differential equation. And then we can solve for n to get the explicit general solution. So we use log properties to combine the two log terms. We can then get rid of the log by e to the side here. And this would end up being e to the t times e to the c1, which itself is a constant, right? So technically we still have the absolute values, but if you drop the absolute values, you have plus or minus. But then the plus or minus can get absorbed into the constant because it could be either plus or minus, which is why the non-bar version here is just equal to some constant times e to the t. If you multiply both sides by n minus 2000 and then gather the n terms over here and factor out the n and then divide, you end up with this as the general solution. Okay, to establish the constant, we'll need to use the initial condition. So the initial condition was that at time 0, we started with one supermarket that had the new checkout system. So when we plug in 1 for n and 0 for time, we end up calculating that the constant is negative 1 over 1999. And when you plug that in here and here, you end up getting this, which if you multiply both top and bottom by 1999, you get this right here. And this is the classic form of a logistic curve, right? You have an exponential function on top and a constant plus or minus an exponential on the bottom, plus specifically, okay? Now, this is the solution. If we were to graph that solution, say in a calculator, we can graph it. Sure enough, it's going to have the curve shape that we saw in our logistic curve sketch from the phase portrait. And down here, it approaches 0. Actually, it goes through the point 1, the supermarket at time 0. But if you go out here, eventually, we approach the value 1998.77. It seems like it's approaching 2000, which is our critical value up here. So this matches what we're seeing. All right, so those are just two examples of how nonlinear differential equations can be used to model. Like I said, we won't focus too much on it because the work of doing it is more complicated, but we'll see it here and there.